80 years. It takes an average of 80 years after your death for everyone to forget about you. Every accomplishment, relationship, and impact you have on the world will be essentially meaningless just 80 years after your death. But that doesn't stop people from trying. Trying to increase those 80 years as much as possible. Trying to leave their mark in the world. Trying to achieve something big. Something like reunifying and sponsoring the freedom of a nation. Something like discovering the fundamental principles of reality. Something like making a YouTube video explaining the physics of a fictional character from the Sonic franchise. Anyways, you're not here for the philosophical or inspiring storytelling, you're here for the physics. Or maybe you're just here for the editing, or the silly jokes. Or you're here because fate simply brought you here, Max. That's right, Max, I know you're listening. I know all about you. I know where you live. We already covered Sonic and Tails, so this time we'll be looking at our flying, fire-colored friend, Knuckles. It's Knuckles. We're gonna do Knuckles. Now, what are we gonna analyze? What's the most impressive thing this Emerald Protecting Echidna did that showed the most strength? While procrastinating on this question, I decided to watch the third Sonic movie when, alas, an absurd, astounding, and astonishing action abruptly absorbed my actively ardent attention. Near the beginning of the movie, a car is launched directly at our freaky friends. Can you guess what happens next? That's right, the credits roll. Just kidding, Knuckles catches it and throws it aside. Yeah, I tricked you real good. I can't believe you fell for that. But yeah, we're gonna see how strong this cherry-flavored fella has to be to perform such a feat without even breaking a sweat. But before we get started with the physics, I think a little roadmap would help with actually knowing what's going on. Let's start on some familiar ground. I think you and I can agree that this car, flying through the air, is a projectile. And as such, we'll first be covering some basic things about projectile motion that will definitely come in handy. Once we get a good understanding of how projectiles move, we'll want to find the exact speed of the car, just before Knuckles catches it and starts showing off to the audience. From here, we'll find the car's momentum. And after a bunch of physics jargon and some calculations, we'll eventually reach our goal, finding out how much force Knuckles exerts to catch a car that's flying through the air. I haven't figured out what the video title is going to be yet, but before we get too ahead of ourselves, let's talk about projectile motion is going to be a big part of this video, but thankfully it's actually really simple and intuitive to work with. I think knowing a few basic properties of projectile motion will give a lot of useful insight, so let's just get into it. I'll be using a projectile motion simulation from a website called PhET. They have some really good simulations for physics, math, chemistry, stuff like that. I'm not sponsored, they're just really good. I'll put some links in the description if you're interested, or if you just want to play around with it. Alright, I've stalled long enough. Let's see a projectile in motion. A lot just happened there, so let's analyze it piece by piece. We're gonna find some pretty important stuff here, so I'll give you an important box of projectile motion trademark to keep all the important stuff we'll find so we can use it later. Anyways, these green arrows are the ball's horizontal and vertical velocity, and this yellow arrow is the ball's acceleration. Oh, by the way, velocity is just physics terminology for speed with the direction. This is so that backwards speed can be considered negative, so it's really handy with calculations. Now, if we look at only the yellow acceleration arrow, we can see that there is never any horizontal acceleration. When an object accelerates, it changes speed. That much makes sense. So, without any horizontal acceleration, we can tell for certain that the horizontal velocity, or speed, never changes throughout the entire trajectory. That's going to be important, so let's put that in the important box. What, you think I'm making this stuff up? Well, maybe you don't, but here, I'll prove it anyways. Look at this. So, if we use this, what am I supposed to call this? A measuring thing? Anyways, if we hover over any part of the trajectory, we can see the time it took for the ball to get there, alongside its horizontal and vertical distance. If we ignore the height, we can see that the range, or horizontal distance, increases by the same amount every 0.1 seconds. In other words, the same distance is traveled in the same amount of time, so the horizontal velocity is the same throughout the entire trajectory. It never changes. While we're here, let's take a look at something else. If we ignore the range this time, we can see that the time it takes to get to the highest point or apex of the trajectory is exactly half the time it takes to reach the ground again. In other words, the apex marks the halfway point in the trajectory. With these two things in mind, let's watch the Sonic movie and finally find the car's speed. In the movie, the car being thrown is identical to what we saw in the simulation, except now we're trying to find exactly how fast the car was moving just before our courageous car catcher caught it. But how are we gonna do a thing like that? By guessing. Wait, let me rephrase that. Where is it? Oh, here it is. By employing educated approximations paired with fundamental kinematics equations based on the complex yet predictable behaviors and properties of projectile motion. So, yeah, by guessing. The easiest way to find the car's speed as Knuckles catches it is to find both the horizontal and vertical components of the velocity here. I'll call this the final velocity since it's at the end of the trajectory. Let's start with the horizontal component, aka the final horizontal velocity. This part isn't too complex since we can just take the distance between Shadow and Knuckles and divide it by the time it takes for the car to reach Knuckles. This will give us the average horizontal velocity throughout the entire trajectory. But that's the average velocity, we want the final velocity. This is no problem though, since our important box shows us that the horizontal velocity never changes throughout the entire trajectory. This means that the average velocity is the actual velocity for the entire trajectory, including the end. I told you this stuff was important. Alright, back to the equation. The time is simple enough. We just measured the time between the hit and Knuckles catching it, which is exactly 3 seconds, surprisingly. The hard part comes with the distance. See, there's no way to tell exactly how far the car has traveled. I mean, we can't even see where the car was thrown in the first place. This is where the guessing comes into play. Here's what I've come up with. Just before the team lands, there's a perfect shot of the area, and we're going to use it to measure the distance. Based on the direction they're moving, this smoke over here, the general shape of the buildings here, and mostly this crosswalk that they're right in the middle of, I know that the team must have landed here. The car is then thrown from behind them from inside all of this smoke here. The car takes a moment to appear after it's thrown, so I'd say Shadow was standing about here. From here, we just connect the dots and measure the distance. Let's see, that's about 30 centimeters. Oh wait, that's definitely wrong. We need a more accurate ruler designed for this specific shot. And believe it or not, it's been right in front of us this whole time. That's right, it's this car. I'm not making this up. See, regular cars like this one, I'm assuming, tend to be around 5 meters long, give or take. So if we take a bunch of these cars and line them up bumper to bumper, we can get a very rough guess as to how far the car was thrown from. Rounding down because of the perspective gets us about 65 meters. Now the easy part. We just put all the numbers in, grab the calculator, and get about 21.89 meters per second as the final horizontal velocity. With that taken care of, our next step is dealing with the final vertical velocity, which can actually be calculated really easily with this equation. That's right, we only need gravity and the time that the car is in the air. That's it. But I'm not going to just give you the answer. I'll prove it. Let's start with the first kinematic equation. By the way, kinematic equations are just physics equations that have to do with basic motion, like what we're seeing in the movie. This one in particular states that the final vertical velocity is equal to the initial vertical velocity plus the vertical acceleration and time multiplied together. This is a bit too complicated though, so let's simplify it. We can get rid of the initial vertical velocity by making it equal to 0. We can do this by pretending that the car starts at the apex of its trajectory, since this is when the car stops rising and starts falling, so its vertical velocity at that instant is 0. This also has the consequence of changing the time variable, since this is no longer considering the entire throw, some of it is cut off. This is where we reach back into our important box, which shows us that the apex marks the halfway point of the trajectory. We're only looking at the stuff after the apex, which is after the halfway point. This means that time has to be divided by 2, creating our original equation. Now, let's put all the numbers in. Gravity accelerates everything downwards at 9.8 meters per second squared, and earlier we got a time of 2.97 seconds. Shoving everything into the calculator gives us a final vertical velocity of about 14.55 meters per second. That's all there is to it. With both final velocity components, we can now use the Pythagorean theorem to combine them into the total final velocity. Doing this reveals that this primary colored punching machine effortlessly stopped a military-grade car flying at 26.28 meters per second. That's pretty fast, but what does that mean in terms of strength? Well, what first came to mind was momentum. Momentum is really handy here, since we can really easily turn it into impulse, which we can then turn into the force that Knuckles exerts on the car, which is already the final goal of the video. That's right, we're in the final stretch. Let's do this. First, let's find the car's momentum the millisecond before Knuckles catches it. Momentum is basically how much motion an object has, and it can be calculated simply by multiplying the object's mass by its velocity. That's it. We just found the car's velocity to be 26.28 meters per second, leaving only the mass. To find the mass, we'll have to figure out what kind of car this is. It seems to be a military-grade vehicle that looks really similar to this one I found online, so we'll be basing the car off this one. But if I'm wrong and they are actually using a different vehicle, then let Zeus strike me down.
If I'm lying. Hey, didn't strike me though.
This is an HMMWV M1114 military vehicle, at least according to the 5 minutes of research I did. These models tend to weigh 5,489 kilograms, or about 12,100 pounds. This is according to the Army Recognition Group, for the 3 of you who care, link in the description. Multiplying the mass we just found and the velocity from earlier, we get 144,264.23 kilogram meters per second for the car's momentum. Wow, that was way easier than finding the velocity. Let's keep this trend of easy calculations and move on to the next step, turning the momentum into impulse. Impulse is just how much momentum changes in a collision, and it can be calculated by taking the difference in momentum just before and just after the collision. That's the final momentum minus the initial momentum. When catching the car, the initial momentum would be just before Knuckles comes in contact with the car, and the final momentum would be just as the car comes to a stop. The initial momentum is what we just calculated, and the final momentum is 0, since the car would have 0 velocity. Knuckles brought it to a stop. Taking the difference gives us negative 144,264.23 kilogram meters per second for the impulse. The negative makes sense because Knuckles is stopping the car, so he's decreasing its momentum, so the change in momentum is negative. But for simplicity's sake, let's just keep it positive, it won't make a difference. But wait, this is the same as the momentum, why bother calculating the impulse at all? Well, the momentum is how much motion the car had, and the impulse is what Knuckles did to change the car's momentum. We need to make this conversion to turn the car's motion into Knuckles' strength, so we can make calculations about Knuckles, not the car. Alright, impulse and momentum. They're cool and all, but how do we turn this into force? If we're going to turn impulse into force, then allow me to direct you to these units we've been ignoring. This is just kilograms multiplied by meters per second, pretty self-explanatory. But if we multiply this by seconds over seconds, we get kilograms times meters per second squared times seconds. This becomes mass times acceleration times seconds. And thanks to some very old and very dead guy called Isaac Newton, we know that mass times acceleration equals force, which is measured in newtons. This means that our impulse can be written as this many newton seconds. And based on our units, to turn this into force, aka newtons, we just need to divide this by seconds, aka time. Just for clarification, the time I'm talking about here is the quote-unquote recoil time, when Knuckles catches it, not the car's air time. Impulse deals with the actual collision, so the time needs to deal with the collision too. Anyways, timing how long the catch takes to bring the car to rest gives us 0.38 seconds, which is the very last piece of this echidna-shaped puzzle. The average person, like you and me, can exert a maximum of around 2,000 newtons of force when catching a really heavy object before straight up hurting themselves. But the Bloat Thrower, Independent Flower, Magical Emerald Holder can catch a military-grade vehicle from midair, effortlessly exerting 379,643 newtons of force in the process. That's a lot of force, and I mean a lot of force. Apollo 11, the spacecraft that first landed on the moon, produced 33.4 million newtons of force to escape Earth's orbit. And this ketchup-covered creature exerted 1.1% of that to catch that car. I mean, that's still impressive, but I kinda expected more from him, especially with him always being so full of energy. That's the thing, Knuckles does all of this no sweat, he even shows off to the audience. It's like this is nothing for him, which it is. Meaning that to show how strong Knuckles really is, we need to push him to his very limit. This part can get a little complex, so try to keep up. A little later in the movie, Shadow drops a mini black hole near Team Sonic, so Knuckles bites an industrial-sized phone charger before eventually reaching his limit and letting go. This is his breaking point. To find the force he exerts, we need to find the gravitational force that the black hole exerts on the team, which we'll calculate using Newton's law of universal gravitation. But since Newton didn't know about general relativity, we'll need to add this part to compensate. Let's deal with one variable at a time. The gravitational constant is just this number, and the mass of the team is 35, 20, and 40 kilograms for Sonic, Tails, and Knuckles. Plus, let's say 55 kilograms for the chains and metal thing, which is 150 kilograms in total. Skipping the black hole's mass, the distance between Team Sonic and the black hole can be best measured using this shot. Using Sonic as a base measurement, we've got a distance of 9.5 Sonics, or 9.5 meters, since Sonic is exactly 1 meter tall. Next, to find the black hole's mass, we can use this equation. The Schwarzschild radius is the radius of the black hole based on the event horizon, aka the edge of the black part. The black hole grows over time, and Knuckles lets go a while after this shot takes place, so we'll have to consider this shot instead. I can't get a perfect estimate because of the perspective and the black hole's uneven shape, but based on the size of Knuckles, I'm guessing that the radius is around 2 meters. This only leaves us with the speed of light and the gravitational constant, which are both just constants. This gives us a black hole with a mass of this many kilograms, which is well over 200 times the mass of Earth. With the mass taken care of, we've got everything we need to solve for the black hole's gravitational force. Putting everything in the calculator reveals that Knuckles, who mind you does not chuckle, can resist 3.8 times 10 to the 18th newtons, or 3.8 billion newtons, using only his teeth. Having that much bite force, it seems impossible, but it's not. That's because Knuckles is a video game character.